My presentation is on the chemistry of immunosuppressive drugs. Okay, so I chose to talk about this topic because it was just like a relevant topic for me because I've had an autoimmune disorder for 5 years, and I've never actually like looked at what's in the medicine that I take, as bad as that sounds. So I decided to take the opportunity to like see how the drugs I take like interact with my body and like keep me healthy. So, how do immunosuppressants work? So, immunosuppressants work by decreasing or halting immune responses in your body in order to prevent the immune system from accidentally harming organs or other bodily structures that shouldn't be targeted. And they can be used for the treatment of many different things, such as autoimmune disorders, organ transplant receivers, and bone marrow transplant receivers. And then here's a video on transplant receiver treatment.
Immunosuppressants. It is very important to take your immunosuppressant medication on time. Learn more about why it is so important for you to follow your medication schedule after transplant surgery. The word immunosuppressant is made up of two parts. Immuno means the immune system, the body's natural defense mechanism. Suppressant means the type of medication that helps to weaken or hold back a response. Immunosuppressants are also called anti-rejection drugs. Your immune system's everyday job is to monitor what gets in your body. It gets rid of anything that does not belong to your body and can do harm to your health. When you have transplant surgery, your immune system believes your new organ does not belong to your body. Taking immunosuppressant medication will protect your new organ. Immunosuppressants affect your body's immune system so it sees the new organ as part of your body. When medication is skipped and the level of immunosuppressant is not enough, the immune system very quickly starts thinking the new organ does not belong to your body. Then, the immune system starts attacking the new organ, thinking it does not belong to your body. The immune system usually does not cause large damage all at once. Rather, your new organ gets small injuries every time it gets attacked. When there is enough immunosuppressant again, the immune system stops attacking the new organ. If immunosuppressant medication is not taken as scheduled, little injuries keep happening to the organ and the damage can build up. This is what happens when medication is taken as scheduled. The immunosuppressant level in your body goes up and down depending on the time of the day, but there is always enough to keep the immune system from injuring the new organ. When medication is not taken as scheduled, the immunosuppressant level is not enough to keep the immune system friendly. Even though medication is taken later on, there will be a time period when the immune system becomes unfriendly and starts attacking the new organ before there is an adequate level of immunosuppressant. You will not likely notice anything happening to your new organ when little damage is done each time. In fact, by the time symptoms are noticed, the organ has already been damaged so much that it may never be healthy again. If you take the immunosuppressants as your transplant team has scheduled, your body should have enough so the immune system keeps thinking the new organ is part of your body. You will need to keep taking the immunosuppressant medication for the rest of your life. If it is done right, you can prevent the immune system from causing injuries to your new organ. You are a very important part of a successful transplant. By taking your immunosuppressant medication on time and making it a habit, you are increasing the chances your new organ will be as healthy as possible for many years to come.
Okay, so what is an autoimmune disorder? So the immune system is normally supposed to locate and eliminate any foreign objects or entities that could be harmful to the body, like bacteria or viruses. But when someone has an autoimmune disorder, the body mistakenly turns on itself and attacks specific areas depending on which disorder you have. So, some examples of autoimmune disorders are Crohn's disease, lupus, rheumatoid arthritis, and psoriasis.
Let's get into autoimmune diseases, what they are, what they do, and the facts you need to know your body. Here's the breakdown. Our immune system is a network of special cells and organs that protect the body from disease and infection. The immune system can tell the difference between self and non-self, basically what's you and what's foreign. With an autoimmune disease, there's a glitch, and your body can't tell the difference, so it makes autoantibodies that attack healthy cells by mistake. There are over 80 different types that can affect almost any part of the body. Some common ones are rheumatoid arthritis, type 1 diabetes, lupus, celiac, Hashimoto's, and multiple sclerosis. Statistics vary on how many Americans have an autoimmune disease, with the National Institutes of Health estimating 23.5 million and AARDA quoting 50 million. One reason for the difference is how many types of diseases are included in the data counts. Symptoms are as vast as the parts of the body and can include fatigue, muscle aches, fever, depression, and inflammation. It can take a lot of visits to a lot of different specialists to be able to find the right diagnosis. A specialist focuses on treating diseases of a particular system of the body. A rheumatologist treats diseases affecting the joints and connective tissue. A neurologist deals with the central nervous system, and gastroenterologists treat the intestines. The causes of autoimmune diseases remain a mystery to solve, but there are some connecting factors. They can be inherited, so we know genes play a part, and environmental triggers like an infection or chemical exposure can sometimes create an autoimmune response. They're more common in women than men, and some tend to affect certain groups of people. Type 1 diabetes is more common in Caucasians, while lupus is most severe for African Americans and Hispanics. Treatments differ depending on the type of disease, so let's talk to an expert. Dr. Lakshan, what are the treatment options for someone with an autoimmune disease, and is there a cure?
Well, there's not really a cure, but in terms of treatments, we have anti-inflammatory drugs, corticosteroids, antimalarials, and we have drugs called immunosuppressives.
So basically those drugs just keep the body from attacking itself, right?
That's the aim of those drugs.
I've read that diet could impact autoimmune diseases. How do lifestyle decisions factor in?
Well, diet works in two ways. Some people think that diseases are actually driven by things that you eat or things that you encounter in your environment. There's no single answer for every patient. You have to experiment.
It sounds like autoimmune diseases play by their own rules, so how can we win?
The best way is to have doctors talk to doctors from one specialty to another to describe and compare and evaluate the patient all as one team.
Thank you, Dr. Lakshan. This has been incredibly helpful, and I hope we've helped you to know your body.
Okay, so there are many different categories of immunosuppressants like corticosteroids, biologics, IMDH inhibitors, etc. The type that would be used on a patient depends on if they had a transplant or if they have an autoimmune disorder. An example of what would be used to treat a patient with an autoimmune disorder would be a drug in the thiopurine category.
Welcome to our second video lecture on immunosuppressant drugs. Today we'll focus on thiopurines. An example of thiopurine is Azothioprine, which is a prodrug of 6-mercaptopurine. If we look at the structure of azothioprine, we can see that it resembles the purine nucleotide. When administering azothioprine to a patient, we administer it orally, and for some unknown reason it takes months for the drug to take effect. Now we're going to dig in and look at the metabolism of azothioprine and 6-mercaptopurine. When administering azothioprine, it is converted into 6-mercaptopurine within the body, and this drug can be shunted down 3 different pathways. It can either go down the main pathway and get converted into 6-thioguanine nucleotides, which is an active metabolite that leads to immune suppression. Therefore, this pathway here is the pathway of interest. Or it can get shunted down this pathway right here through an enzyme called thiopurine methyltransferase and get converted into an inactive metabolite 6-methylmercaptopurine, or it can get shunted through this enzyme here, xanthine oxidase, and get converted to an inactive metabolite 6-thiauric acid or other oxidized metabolites. Now, why am I telling you about these two enzymes here if they don't lead to immune suppression? Well, the reason I'm telling you about these two enzymes is because, first of all, when a patient comes into the hospital and they have gout, increased levels of uric acid, they'll probably be on a medication called allopurinol. Allopurinol will inhibit xanthine oxidase and therefore shunt 6-mercaptopurine down this main pathway. Likewise, thiopurine methyltransferase is a primary example of pharmacogenetics. Some people will have decreased activity of this enzyme, and therefore we will also get a shunting of 6-mercaptopurine down this main pathway of interest right here. By shunting 6-mercaptopurine down this main pathway, we will have increased levels of thioguanine nucleotides, and therefore we will have increased immune suppression and increased adverse drug reactions if the doctor doesn't take into account if a patient is on allopurinol or if they have decreased activities of thiopurine methyltransferase. An important thing to remember is that before administering this drug, a clinician will always measure TPMT levels to make sure that the patient doesn't have a genetic defect. Now, how does this drug work? Well, it leads to a depletion of purine nucleotides, which are important for cell survival, replication, and gene expression. This will result in apoptosis of activated lymphocytes. The uses of azothioprine are many. Initially, it was used as an anti-leukemia drug. However, now these days there are much more potent and much more reliable drugs that are used instead. However, it is still used for rheumatoid arthritis, inflammatory bowel disease, autoimmune hepatitis, and prevention of transplant rejection. Now we're going to look at some of the adverse effects of azothioprine. We have early adverse drug reactions, which constitute opportunistic infections, which, as I mentioned in the first lecture, is a common theme among all of these immunosuppressant drugs. And I'll repeat it, an opportunistic infection is an infection that is either abnormally severe or a normally healthy person wouldn't get it. We will also get bone marrow suppression, which can lead to leukopenia. This makes sense, as we are interfering with gene transcription and also cell replication. And therefore, because we are interfering with this, the cells within the bone marrow, since they are actively dividing and they're actively expressing genes all the time and very quickly, we will lead to suppression of these cells and therefore can lead to decreased amounts of these cells within the blood. We can get idiopathic pancreatitis and also allergies such as fever or skin rash. Some late adverse drug reactions are also opportunistic infections, idiopathic liver injury, and Epstein-Barr virus associated lymphomas. Epstein-Barr virus is a cancer-causing virus which 95% of us have been exposed to. Welcome to
Okay, so the previous video showed the chemical makeup of an immunosuppressant used for people with autoimmune disorders. Well, it's mainly used for autoimmune disorders. I know it can be used for transplant receivers as well. So now we're going to look at a immunosuppressant that's primarily used for those who have received an organ transplant.
Hello, in this video we're going to talk about the pharmacology of calcineurin inhibitors. Calcineurin inhibitors such as tacrolimus and cyclosporin are immunosuppressants. They are used mainly to prevent organ transplant rejection in combination with mycophenolate and steroids. It can also be used for severe atopic dermatitis. They're not really used as much for rheumatological conditions anymore. Possibly can be used for lupus nephritis. Calcineurin inhibitors essentially inhibit the synthesis of interleukin-2. Normally, antigen-presenting cells, such as macrophages, picks up an antigen, a new one, either foreign or a self-antigen, processes it, and then presents it on an MHC class 2 molecule towards T cells. Now, these T cells will become activated, and they require interleukin-2, a key autocrine T cell activator. Activation of T cells will stimulate the adaptive immune response, consisting of cytotoxic T cells, T helper cells, and then they will also activate plasma cells, the antibody-producing cells. Calcineurin inhibitors inhibit calcineurin, a key protein required to allow transcription of interleukin-2, the key autocrine T cell activator. The mechanism of action is a bit more complicated. Let's take a closer look at how naive T cells become activated. So an antigen is presented to T cell receptors, which will initiate a cascade of intracellular events. This begins with activation of phospholipase C. Phospholipase C hydrolyzes phosphatidylinositol 4,5-bisphosphate, also known as PIP2, to generate the secondary messengers inositol 1,4,5-triphosphate, IP3, and diacylglycerol, DAG. IP3 increases intracellular calcium levels. Calcium binds to calmodulin, later binding to calcineurin, a calcium calmodulin dependent phosphatase. Calcineurin, when it's bound to all this stuff, dephosphorylizes nuclear factor of activated T cells, NFAT, which when dephosphorylated targets the interleukin-2 gene to make interleukin-2 cytokines. Interleukin-2 is released by the T cells, which in turn acts as an autocrine molecule binding onto interleukin-2 receptors on the surface of the T cells. Interleukin-2 will activate this T cell and eventually will initiate the activation of the adaptive immune system. Cyclosporin is a calcineurin inhibitor, which works by binding to the intracellular receptor cyclophilin-1, producing a complex known as cyclosporin-cyclophilin. This complex subsequently inhibits calcineurin, which in turn stops the dephosphorylation as well as the activation of the nuclear factor of activated T cells. Tacrolimus is the other calcineurin inhibitor, which binds to an intracellular protein called NKBP12. It then continues to form a complex consisting of the tacrolimus FKBP12, calcium, calmodulin, and then later calcineurin, which will inhibit the phosphatase activity of calcineurin. And when the phosphatase activity is inhibited, the NFAT doesn't get dephosphorylated. Calcineurin inhibitors have a number of side effects: hyperuricemia, increasing the risk of gout, nephrotoxicity, hypertension and hyperlipidemia, as well as hyperglycemia. The side effects are more common in certain types of calcineurin inhibitors. For example, hyperglycemia is more common with tacrolimus. Hypertension, hyperlipidemia, and hyperuricemia is more common for patients using cyclosporin. I hope you enjoyed this video on calcineurin inhibitors and their mechanism of action. Thank you for watching.
And with that last video, that is the end of my presentation. I hope I was able to teach you a thing or two, and thank you.